Okay, welcome back. So today we're going to continue on with probability, and we're going to go through the last few topics, which are going to cover Venn diagrams and tree diagrams. And then the last thing we're going to talk about are contingency tables. And that's going to be the last section of this chapter, chapter 3 on probability. Okay? So the first thing I want to do is just talk about tree diagrams and Venn diagrams. So a tree diagram and a Venn diagram are both visual displays to help us understand how to look at probabilities. It's an easy way to figure out what the sample space looks like, all possible outcomes. It's also a way to show us how to deal what the probabilities are for a particular outcome and how to use the addition rule and the multiplication rule. So the tree diagram is a great way to do that. Also, the Venn diagram is another way of visualizing probabilities and how they events relate to each other. And so I'm going to use those in a couple of examples. So this is going to be a pretty straightforward video. So there's only going to be a couple of examples for each one, and then we're going to just leave it at that. But it's a way to use their tools to help you solve probability problems and to help you realize how to use the multiplication rule and the addition rule and when they're appropriate. The setback or the restriction on using these visual tools is that they're only useful for small experiments with a certain number of trials or steps, if you will. So with that in mind, they can get cumbersome when we start doing multiple steps, and you'll see why in a moment. But let's do an example. So the first thing is a tree diagram, and we'll start with that. Now, and you'll see where it comes from as soon as you see me draw out the diagram. So let me grab some of my markers. So we'll start with a tree diagram. Okay, so here's a tree diagram. So a tree diagram looks like a tree, a bunch of branches. Okay, so let's take an example. And let's say we have an urn. We have an urn of marbles, and in the urn we have 11 marbles, okay, or 11 balls. We have 11 balls. So in the urn, we have 8 blue marbles and 3 red marbles. And so what do? We're going to take 2 balls, one at a time, with replacement, which means we're going to take the ball out, write down the color, put the ball back in. Okay? And we're going to use the tree diagram to figure out not only what the total possible outcomes are, but what are the probabilities of each outcome. So what are we going to do? We're going to draw 2 balls. So there's 2 steps in the tree. Okay, so in the first draw, so we'll have 2 branches, right? So because how many outcomes do we have on the first draw? We have either a red or a blue, right? So those are the 2 colors. So our tree starts out with 2 branches for the possible outcomes on the first draw. Okay, so I'm just going to write out here first draw. Write it out a little further. Okay, so there's the first draw, and I can either get a red or a blue. Now in the second draw, in either case, whether I get a blue on the first draw or whether I get a red on the first draw, I'm going to have 2 possible outcomes for each case. So what happens is, for the second draw, I'm going to end up branching out 2 possible outcomes for this one, and 2 possible outcomes for this one. So I could get a red or a blue in this case, right? So this is the second draw. Okay, so I could get a red or a blue here, or I could get a red or a blue here. So this is the tree diagram for this experiment. Okay, so what are the possible outcomes? Well, I just go down each branch, and that's going to be a possible outcome. So if I go down this branch, I could get a red and a red. If I go down this branch here, I could get red and then a blue. And then if I go down this branch here, I could get a blue and then a red. And then I could go down the final branch and end up with a blue and a blue. So those are the possible outcomes. Okay? So, now, so here's what these outcomes represent. This represents that I got a red on the first draw and a red on the second draw. A red on the first draw, a blue on the second draw, blue on the first draw, red on the second draw, blue on both draws. Okay, so those are the possible outcomes. Okay, now, how do we do the probabilities? Well, look at this is where the replacement comes in, right? So on the first draw, what's the probability of getting a red? Well, how many reds do I have? I have 3 out of 11. So that probability here is going to be 3 out of 11. So I would just write 3/11ths on that branch. And so then the probability of getting blue then would be 8 out of 11, right? Now here's the thing. On the second draw, how many balls do I have available to me? Well, I have 11 because I'm replacing the ball back in. So I still have 11 balls to choose from. So once I have the first draw out of the way, well, what's the probability of getting red or blue on the second draw? Well, it's going to be exactly the same. So here, it's going to be 8 out of 11 again, or excuse me, 3 out of 11. This will be 8 out of 11. And then, of course, again, it'll repeat 3 out of 11 and 8 out of 11. Right? So now I've got my probabilities set up. Now, what's the probability of getting a red on the first draw and a red on the second draw? Well, the way we figured out those probabilities is we multiply down the branch. So what branch do we multiply down? We multiply down the first branch. So we take 3/11ths times 3/11ths, and we get a probability of 9 over 121. That's the probability of getting a red on the first draw and a red on the second draw. See how this is the multiplication rule in action, right? Okay, why? Because they're independent events. Why is it that I can just multiply these two together? Because they're independent, right? This is where the simplified rule comes in, right? So all I'm doing is multiplying down the branches. That's the multiplication rule, okay? So if I wanted the probability of R and then B, red and then blue, I go down this branch. So it's 3/11ths times 8, right? So 3 times 8 is 24 over 121. And then so on and so forth. If I keep doing this in like fashion, so if I go down this branch, I get 8 times 3 again, which is 24 over 121. And then I go 8 times 8, which is 64. Oops, let me do this right. Yeah, that's right. 64 over 121. And those are my probabilities. And notice, okay, notice that if I add up all of these numerators, they add up to 121. So I know I've got a valid probability distribution because I know I have 121 possible outcomes. Why is it 121 and not 4, right? Because I only got 4 outcomes here. Well, these are not all equally likely. Remember, I've got 8 distinct balls to choose from here, 3 red distinct balls to choose from. Okay, so I end up with a total possible number of outcomes of 121. Okay, so let's see here. Yeah, that's it. That's pretty much it for the tree diagram. So now, with this here, let's do, now here's the thing, let's also consider the distinct outcomes because we have, remember, 121 distinct outcomes. Why? Here's how you see it. Let me just do it this way. Let's put a number so you can see it better because again, every ball is distinct, right? There's 3 red balls. I could choose any one of those 3 distinct red balls. So let's pretend we put a number on each one of those balls so we can actually see all the possible outcomes together, right? So here's how we're going to do that. So we have red, so let's call red 1, red 2, red 3, right? And then we have blue 1, blue 2, blue 3, blue 4, blue 5, blue 6, let me do it this way, blue 7, and then blue 8. So now I've got those outcomes, okay? Now, so red and then a red, right? So I could get a red and then this red, right? So that's one outcome. I could get this red with this red, that's 2, right? And then I could get this red with itself, right? Because I'm doing replacement, right? So I could get the same ball out twice, right? So I can get this one twice, that's 1. I can get this one and this one, that's 2. I can get this one and this one, that's 3. And then I can move down. I can get this one and this one, that's 4. And then I can get this one and this one, that's 5, right? And then I can get this one and this one, that's 6, right? But then I can get this one first and then this one, or I could get this one and then this one. And that brings me up to 9. Okay? And then this one and this one too. That's right. So I can do this one and this one. That brings me up to 9. So there you go. So I'm just using that one example, but then any one of these, that's how we get the 9. Now you can do the same thing for R and B and R and B. You can, do the pairing. It's just how many different ways can we pair, and order matters, right? So that's where the 121 possible outcomes come from, okay? They're distinct outcomes, okay? So I hope that makes sense. So this is an example of how we can use a tree diagram. So now let's answer some questions, okay? So the first one says, list out the 24 BR outcomes. Well, you guys can do that on your own. I just did it for RR. So let's list out for just the getting red. That'll be easier. I'll let you guys do the rest if you want on your own. In fact, it'd be instructive to do the RB, see if you can come up with the 24 outcomes based on what we wrote here. So here are the 9 outcomes for getting RR. Okay, so I can get R1 followed by R1, right? Because of replacement. I can get R1 followed by R2. I can get R1 followed by R3. I can get R2 followed by R2 again. And then I can get R2 followed by R3. And then I can get R3 followed by R3. So now, that's the first 6. Now the last 3 is I'm going to switch some of these. So I can switch these, so I can get this one, right? So that's going to be R2, comma, R1. That's one way. I can switch these two, so I could get R3, comma, R1. And then this one here, I could switch. So that's R3, comma, R2. Okay? So now, those are all 9 of the possible outcomes, okay? And any one of these outcomes will give me RR, okay? So that's where the 9 out of 121 come from, okay? And you could do the same thing for any one of these, okay? So that will answer the first part. Now, using the tree diagram, calculate the probability of RR. Well, we just did that, right? We just went down the branch. There it is, 9 out of 121. See how easy that was? So once you have the probabilities set up on the tree, you just multiply for that one. Now, the next one says, using the tree diagram, calculate the probability of RB or BR. Ah, okay, so let's get rid of this. And so how would we do that one? So we want the probability of RB or BR. Well, the question is it's or, right? So we want to ask ourselves, are those events mutually exclusive? Can they happen at the same time? Can we get RB and BR at the same time on one trial of the experiment? And the answer is no. We can only get one or the other. Well, now we could use, since they're mutually exclusive then, right? They can't happen at the same time, which is by definition, they're mutually exclusive. That means that we can use the simplified multiplication rule, which would then just be the probability of RB plus the probability of BR. And so what are we going to do? We're going to take these two probabilities and add them, right? Because these two branches are mutually exclusive. Branches are always mutually exclusive. You cannot jump from one branch to the other. They're mutually exclusive, right? So if I want the probability of this or this, we're going to add across branches, okay? So that means we're going to take 24 over 121 plus 24 over 121, which equals 48 over 121. And that's it. See how easy that is? Okay, now, what about it says, use the tree diagram, calculate the probability R on the first draw and B on the second draw. Okay, let's look at that one. So now it says, probability of R on the first draw, there's my subscript 1, and B on the second draw. Well, this is an and statement, right? So R on the first draw, that means here, and B on the second draw. Well, where are we going? We're going here and then here. So we're going to go this times this equals this. So it's just going to be, because of replacement, again, we're just going to go down the branch. Replacement or not replacement, actually this is just the rule. So we just go down the branch and multiply. We multiply down the branch, we add across branches. So what we're going to do is we're going to take 3/11 times 8/11, and of course we already have that. We already did that. That's this one right here, right? Probability of gaining red followed by blue. 24 out of 121. So we already had that one, right? Okay, what about the next one? The probability of R on the second draw, given that we got B on the first draw. I like this one. I like this one a lot. Okay, so this is a conditional probability. It says the probability of getting a red on the second draw, given that we got a blue on the first draw. Okay, so that means, what's the given information? We know we got a blue on the first draw. That means we're here. Okay, so we can ignore this half of the tree. So that means we're over here. So we know we got a blue on the first draw. Now, what's the probability of getting a red on the second draw, given that we already know that we got a blue on the first draw? Well, it just becomes the probability of red. Because if I know I'm over here, right, I don't care about the 8 on 11. I already know I got it, right? So I know I got a blue. So I basically can ignore the first draw. I already know I got a blue. If I already know I got a blue on the first draw, what's the probability of getting a second or getting red on the second draw? Well, it's just going to be whatever the probability of red is. So this is just going to be 3/11. Okay? But let's apply the definition, see if we get the same thing. Okay? So the definition here, right, is the probability of getting a red on the second draw and blue on the first draw divided by the probability of getting what? Blue on the first draw. Okay? So let's think about this. So what's the probability of getting blue on the first draw and red on the second draw? Well, we got that one. So it's going to be blue followed by red, right? So that's going to be here. It's going to be 8/11 times 3/11. So that's going to be 8/11 times 3/11, right? And what's the probability of getting blue on the first draw? Well, that means I could get blue on the first draw here and then get red on the second draw, or I could get blue on the first draw followed by a blue on the second draw. Both of those outcomes would give me blue on the first draw, right? So we have to consider both of those. So that means it's going to be either this one or this one. So it's going to be the probability of this, so this is going to be what? It's going to be 8/11 times 3/11 plus 8/11 times 8/11. Because I have to consider both possible outcomes. Both of these outcomes give me blue on the first draw. Okay? So if I want the probability of getting blue on the first draw, I have to consider this whole side of the branch. Okay? That's where this sum comes up, right? It's going to be this outcome or this outcome. Okay? And I add both of those probabilities up. That will be the probability of getting blue on the first draw by drawing two balls. Remember, I'm drawing two balls. I have to consider all the outcomes for two balls. Okay? Okay, now, what do I do here? Well, what does this equal? This is going to equal 24 over 121 over what? 64 times 24 over 121, right? So what does that reduce to? That reduces to, the 121s drop out, and that reduces to 24 over 64 times 24, right? And what do we get there? Hold on a second. Something's not working out right. I'm messing up here somewhere. So we got this plus this. Oh, that's what I did wrong. It's a plus, not multiplying. I'm adding. That's where I made mistakes. Sorry about that. See? So now we're adding. So it's going to be 24 plus 64. I put multiplication there instead of plus. So now the 121 still drop out. And what do we get? We get 24 divided by what? 64 plus 24, which is what? 88. And so what does 88 reduce to? Well, lo and behold, it's just going to reduce to what? 3/11. So because if we divide the top and the bottom by 3, or by 8 rather, we divide the top and the bottom by 8, we're going to get 3 over 11. And we get the same answer. So much easier just to know how to use the tree diagram. Because again, if you think about it, remember the idea of thinking about it? You know, so a lot of these, we can just like think through the process instead of applying the probability, the definition of conditional probability, we can just kind of think through it. Well, what's the given information? We know we got a blue marble. Well, if we already know we got a blue marble in the first draw, well, we can just ignore the first draw and just focus on the second draw over here. Well, if we're doing replacement, then the probabilities don't change, right? They're independent. So what's the probability of getting red on the second draw? Given that I know that I got a blue on the first draw, well, if they're independent events, it doesn't matter. So that means it's just going to be 3 out of 11. And that's what we got here using the formula. Okay? So that's that question. And the last question is, what's the probability of getting blue-blue? Well, we got that one already. Blue and a blue, that's going to be 64 over 121. Okay? So I hope that helps with dealing with some simple probabilities. It's just another tool in your toolbox. Again, if we were to do 3 draws, you can see how at the bottom here we would end up with 8 possible outcomes down here, so and our branches would start to get congested. So that's one of the drawbacks of using a tree diagram. It tends to get congested at the bottom and hard to manage. It's a little tedious. Okay, it's doable but tedious. Okay, great. So now let's talk about Venn diagrams. So Venn diagrams is another tool that we can use. Okay, so what's a Venn diagram? A Venn diagram is a visual tool that allows us to, again, display probabilities and the relationship between events. Okay, so let's see here. Let's do this. So we start with our Venn diagram with a rectangle. And the rectangle represents our sample space, all possible outcomes. Okay? And then we represent certain events that we define by circles. Okay? So let's set up this here. So this would be one circle, and we're going to call that C. We're going to set up another circle, and we're going to call this PT. Okay? So here's the setup. And again, this is another example of where we can use these. Okay? So let's say we know that 40% of the students at a local college belong to a club, and 50% work part-time. Okay, so this is the event of working part-time. This is the event that they're part of the club. So this circle represents all of the students who work part-time. This circle represents all of the students who are part of the club. Okay, and then of course the overlap is all the students who both are part of the club and work part-time. Okay. So now, how do we display this? Well, we know that, what is it? 40%, right? So 40% are part of the club. 50% of students work part-time, okay? And what do we have here? This are all the students. So the rectangle represents all of the students at this college, right? So here's the total sample space, right? All the students at the college. Within the sample space, we have students who are part of the club, right? We have students who work part-time, right? Outside of that, we have students who aren't part of the club and don't work part-time, right? Inside here, in the middle, are the students who do both, right? Here, outside of this intersection, are the students who are part of the club but don't work part-time. Over here are the students who work part-time but are not part of the club. Okay, hope that makes sense. Now, let's see here. Okay, now, let's see here. It also tells us 5% of the students at the college work part-time and belong to the club. So, what does that mean? It means that right in here, this is going to be 0.05, right? 5%. So we know that the percentage of students that both work part-time and are part of the club is 5%, 0.05, right? So that's the probability. Which means, what's left over for this piece here? Well, if we know that the total is 40%, and we know 5% is in here, then that leaves 35%, or 0.35, out here. Okay? And then, if we also know that 5% is in here, how much is left over for this piece of this circle for part-time students? Well, it's going to be 0.45, right? Because we know 50% of the students work part-time. So 0.45 plus 0.05 give us the 50 here, 0.35 plus the 0.05 here give us the 40 over here. So now we've got everything set up. Now, what percentage falls outside of both of those circles? Well, we add up all of these percentages, right? So this is 0.35, so that's 40, and then we got another 45 here, 0.45 here, so that gives us 0.85, right? So that means out here we have 0.15 left over, okay? So now let's answer some questions here. It says, the probability that a student belongs to a club given that the student works part-time. So if the student works part-time, right, so now we're in this circle. If we know that the student works part-time, what's the probability that they are part of the club? Well, how do we do that? Well, let's just use the definition here. Probability that a student belongs to a club given that the student works part-time. Well, that's going to be the probability of both, right? Divided by what? The probability of part-time. Okay? Now, what do we do? Well, what's the probability of both? 0.05. What's the probability of being part-time? The whole thing. That's going to be 0.5. And so what's the difference? It's going to be what? 1/10. And that's the answer. Okay? The other way to look at it, remember, what happens when you do conditional probability? It always shrinks to the given event, right? The probability of the given event. So now, as soon as we know that the student works part-time, all we care about is this circle. So what's the new sample space? What's the new probability? The new sample space is the 0.5, the probability, right? So 0.45, or 0.5 is the new probability that goes on the bottom, and then how much of that is in the club? 0.05. So you can do it directly just thinking about it too, okay? Now, what about B? It says, what's the probability that the student belongs to a club or works part-time? Well, the Venn diagram tells us exactly what to do, because in order to do or, right, we need to count up all of the people that are inside one circle, all of the people that are in the second circle, and then remember we have to subtract off the middle piece because we're double counting, right? Because why? They're not mutually exclusive. There's overlap here, right? If you remember from the other video on mutually exclusive events. So what we have to do is we have to take the probability of this circle plus the probability in this circle and then just subtract off the middle piece. So the probability of being part of the club or working part-time is just going to be what? All of these added together. In fact, you don't even have to worry about double counting, right? Because all we're going to do is take these three pieces because it's the union of all the sets. So we take all of the individual pieces and add them up, right? So in this case, all we have to do is add 0.35 plus 0.05 plus 0.45, and we know that that is going to be 0.85. Okay? And that's it. With the Venn diagram, when we have the pieces all filled in, we can just add up the pieces like that. Okay, now the next one, C says, the probability that a student works part-time but does not belong to a club. Okay. So we want the probability that a randomly chosen student works part-time and, right, but is the same as and when it comes to logic. So it says but doesn't work but is not part of the club. That means and, right? So works part-time and is not part of the club. Well, what part of the Venn diagram represents that segment of the student population? Well, works part-time and is not part of the club. That's going to be this piece right in here, okay? And what's that? 0.45. And that's it. And the last one is the probability that a student neither belongs to a club nor works part-time. So a student that does not belong to a club and does not work part-time. So it's and, right? So doesn't, right? Doesn't work part-time, so that's PT prime, does not work part-time, and is not part of the club. Well, what segment of the student population based on the Venn diagram is that? Well, that's going to be everything outside both circles. So that means it's going to be 0.15. And we're done. That's it. Okay, so that's another tool. The Venn diagram is another useful tool to help us visualize probabilities, visualize the relationship between events, and be able to calculate the probabilities for and, or, and the complement rule. Okay, so that's where we're going to stop today. And next time I will continue on with the last section of Chapter 3 of probability, which is going to be on contingency tables. I'll see you next time. Okay, so welcome back, and here's the next topic that we're going to talk about. Excuse me. So this will be the topic on contingency tables. Again, this is going to be a short video just on showing you how to use contingency tables to get probabilities. This is actually a lot of fun for me. I like dealing with contingency tables, especially when it comes to conditional probability and questions like that, and or, and conditional. So I'm going to do a couple of examples, and that's pretty much it. I've done examples with contingency tables before, but I wanted to make a separate video specifically just showing contingency tables. So last time we talked about using tree diagrams and Venn diagrams. So the next part, this is 3.4 in the text, if you're following along in the text, but the topic is just on contingency tables. So contingency tables are used as far as ways of displaying data, okay, to calculate probabilities, to compare variables. That's a common way. You're comparing two variables, and you want to see, hey, what's the probability of a randomly selected person showing both characteristics, or one characteristic or the other, those sorts of questions. But it's a great way of dealing with probabilities. So let's do an example, and then I'll show you what a contingency table looks like, and then we'll go from there. So let me get some other markers. Okay, so let's use some of these. Okay, so let's look at this example. So suppose we have a study of speeding violations. And so what we're going to do is we're going to look at speeding violations and drivers who use cell phones using the following data. Okay, so here's what the study produced. Okay, so we're going to have a table like this, and we're going to expand it out one more. Okay, so this is what we got. Okay, so we have a 3x3 table. So this one is going to be speeding violations in the last year. So this is all going to be based on the last year. So speeding violations, we're going to say, so this is going to be speeding violations. Within the past year. So we're going to have, yes, they did have a speeding violation in the past year, or no, they didn't. And we're going to say cell phone user or not a cell phone user. Okay, so were they using their cell phone? So we're going to have cell phone user. And that'll be yes or no. Okay? So that's what we're going to use. Okay, now, we're going to fill in the numbers here. So the first thing we're going to do is we're going to say we have 25 in this cell, 280 in this cell, 45 in this cell, and 405 in this cell. And so this is going to be our column totals. And this is going to be our row totals. Okay? So now if we add up the columns here, well, we get 70 here. So that's the total of all the people that had speeding violations in the past year. And these are the column of people who didn't have speeding violations, so that's going to be 685. And now for the row totals, we have, for the people who are cell phone users, we have a total of 305. And then for the no on cell phone users, we have a total of 450. And so if we add up the row totals, or if we add up to the column totals, we should get the same grand total, which in this case is going to be 755. Okay? Make sense? Okay, good. So now, this is the grand total. This is what we call the grand total. Okay? This is the total of all the people that were in the study. Okay, so this is your overall sample size. Okay? So now what we're going to do is we're going to use this contingency table. This is a contingency table. Okay? We're comparing people who use their cell phone while driving and whether they've had a speeding ticket in the last year. Okay? So now here's what we do. Let's answer some questions now based on this table. So the first question is we want to find the probability that a randomly selected person is a cell phone user. So C, is there a cell phone user? Okay? And is it S? Let me see. V. V, they've had a violation. A speeding violation. Okay? So that's what we're going to use for the events. Okay? So here, the probability that a randomly selected person has uses their cell phone. Okay? While driving. Okay? Well, actually, it doesn't say whether they're driving or not, but it just says whether they use their cell phone or not. It says C is the event that a person is a cell phone user. Okay, I'm assuming that they use their cell phone while driving. That's what I'll assume that. But anyway, so based on the table, what is the probability that a randomly chosen person is a cell phone user? Well, how many people out of the whole table use their cell phones? It's going to be right here, yes, all the way here, 305. So 305 people are cell phone users over how many people are there in the entire study? 755. And so the probability just turns out to be 305 divided by 755. So let's see here. And it's 0.404. And that's it. Now the next one says, what's the probability that a randomly selected person does not have a violation in the next year or in the last year? Well, how many people did not have a speeding violation in the last year? Well, it's down the no column, so it's going to be 685 divided by what? The total, the grand total, 755 out of everybody. And so if we take those two numbers and divide them, we get 0.907. Okay? And now the next one says, find the probability that a randomly selected person is both a cell phone user and has not had a speeding violation in the past year. So that's going to be cell phone user and not V. Okay, well, based on the table, how many people are cell phone users and have not had a ticket in the past year for speeding? Well, we go across cell phone users, okay, and no for speeding violations. So right here, so we go down this column, across this row, and it's there right there. 280 people fit into that, okay? So that's going to be 280 divided by what? 755, right? It's out of everybody, right? So now 280 divided by 755 is 371, 0.371, 0.371, okay? It's that easy. Using the contingency table just makes it easy, just putting the numbers and you're just, what number goes on top, what number goes in the bottom and divide. So really it's however many people fall into that event divided by the total number of people, right? So this is relative frequency definition, the empirical definition of probability, right? We're just putting the numbers on the top and the bottom and then dividing. That's it. Just using the empirical definition of probability. Okay, so now let's erase this and continue. So now the next question is, what's the probability of not getting a randomly selected person? What's the probability of randomly selecting an individual and that they don't get a speeding violation in the past year, or they're a cell phone user? Okay. Well, now this is either or, right? Or both, right? So, are they mutually exclusive, right? Or you ask yourself, are they mutually exclusive? Can they happen at the same time? Yes, that's what we calculated before, right? Can they happen at the same time? Yes. There are 280 people who attest that, hey, I'm a cell phone user and I have not had a speeding ticket in the past year. So it can happen that it's both, so therefore they are not mutually exclusive. So we're going to have to use the general addition rule, right? So it's going to be the probability of not V plus the probability of C minus the probability of both V, not V, and C. Well, did we already calculate these? Yes, in part A, B, and C, right? So now let's just put it together. So probability of not V, right, is going to be 685 over 755, right? Plus the probability of being a cell phone user is 305 over 755, minus the probability of both, which we found to be 280 over 755. Well, if we just add and subtract over the numerators and divide by the denominator, we're done, right? So if we do this plus this, that gets us 990, right? And then 990 minus 280 is 710. Okay, so we get 710 over 755. Check my math. So we got 990, 710. That's right. And so 710 divided by 755 is 940, 0.940. And that's it. It's that easy. So now let's do a couple of conditional probabilities. Now this is where it gets fun. For me personally, this is where it becomes fun. So now, what's the probability that a randomly selected person is a cell phone user given they had a speeding violation in the past year. So now, the fact that I know whoever this randomly selected person is, I know that they've had a speeding violation in the past year. So that means I'm only interested in the group of people who what? Who have been involved in a speeding violation. So I'm only interested in this column. Everything else on the table you can ignore. So now what happens? My sample size decreases from 755 to now the new total is just the group of what? The group of people who have had a speeding violation, okay? So now, what's my new sample size? It's going to be 70. Now, out of the 70 people who have had a speeding violation in the past year, how many are cell phone users? 25. There's the probability. So now it's 25 divided by 70. So now it's 0.357. Okay, now let's do this one. Let's do the probability that a randomly selected person is randomly selected person does not have a moving speeding violation in the past year, given that they are not a cell phone user. So now, what are we interested in? Well, what's the given information? Well, we know this person, whoever they are, is not a cell phone user. So now we're only interested in the group of cell phone people who are not cell phone users. So that means we're only interested in this group right here. Okay? So now, what happens to our sample size? It goes from 755 to 450. Okay, so now, out of the 450 people who are not cell phone users, how many of them have not had a moving violation? Well, 405. So what's the probability that a randomly selected person is not going to have a moving violation or a speeding violation in the past year, given that they are not a cell phone user? 405 over 450. So it'll be 0.9. Exactly. Does that make sense? So this is the way you would use contingency tables to help answer questions about probability. And I hope that helps. Again, if you have any questions, reach out to me, and I'll see you next time. Thanks.